Thank you. So we've been having a situation yesterday. The student that was going to do the video was sick or something. We have covered something that was sort of complementary, and half of you were there. I know there's some differences. The people that come on Tuesday and Thursday are different than Monday, Wednesday, and Friday. So the two things that we can do is I will point to a lecture. It's almost the same lecture number from last fall. It has a similar content, but for those who are here today and they want to talk about fracture surfaces and polymer processing and all that, I'm going to stay here and I want to show you the sample. It'll only take 5-10 minutes if you're available. So we went through this hardware about forging, and then I had some example on how you analyze the fracture surfaces, which on the video it's hard to do anyway. And it's really just kind of a sidetrack. I spend more time in the spring on failure analysis, but I figured it would help tie in. Okay. So again, it was sort of complementary. This week so far, what we've done is on Monday, we spent time, and I have the schedule here. So we at lecture 7, and I'm doing all this week. I'm going to be lecturing next week only on Wednesday because of the holidays you can have Monday and Tuesday, and then Thursday, Friday, we decided to leave it open so you guys can prepare your student presentation. There's nothing like being ready a week or two ahead. I haven't heard a whole lot about what you guys are planning to do, and today, tomorrow, I'll just stay after class and see if any of you want to talk, or you can send us an email to schedule time. So as far as setting up your student presentation, Professor Eager, you can contact him this way. He may refer to his secretary if you want to schedule an appointment. And I'm here quite a bit this week, next week, the following week. I was just away all of last week, but I'm back. So let us know if you're not in class, if you have a conflict and you do things online. Just chatting about ideas you have. The main advice I give typically for a student presentation is it makes sense for you to take something that you've been involved with before. Just try to take it in a little bit in the context of the class, whether it's Professor Eager's module or my module, kind of thinking, okay, so exactly how those parts were made, or why did they pick this material, for example, and expand on that. And 10 minutes goes by very quickly. So we're not asking you to do, a very extensive research, just, a thought process, and we're happy to help you through that. If you say, I'm interested, how airbags work, for example. Well, we know a little bit. Everybody knows a little bit about airbags, but you have to kind of pick a little aspect of it. Say, I'm going to be looking at, why they're using whatever material they're using. I don't even remember what it is. But and there's been an evolution over time. It's anything you like. We really want to give you the opportunity to just do a little study. With respect to the one-page summary for each module, I believe we were clear. So one is due this coming Monday for your first summary, and Professor Eager was done on Friday. So it gives you about a week to put it together. It's only one page, and it's the same process. Show us that you learned something, whatever it is. If you want to spend a page to talk about the examples you thought that you'll remember, that's fine. If you want to give more of an overview, it's really up to you. And I guess it's part of how it's going to be interesting for us to review that. And personally, I'll be giving you feedback. The last lecture, I'm asking for mine to be done before I'm up to lecture 12. So the last lecture will just go over what it is that you've learned, and maybe you have questions. So it's okay for you to put questions in your summary. There's nothing, and some of these you may decide, oh yeah, that's what I'm going to do my student project on. I think it's just a really, really good learning for me since I graduated 10, 12 years ago now. If I didn't take notes, about, meetings I had, conferences I went through, I think I'll be completely, kind of cruising along, not exactly knowing what I'm doing. So it's just a really good exercise. Say, okay, what did I learn here? And then what do I want to go from here? I don't want to know anything more about this. It's a conclusion, so you move on. You say the other people seem better, or this looks interesting, so I may take another class. It's just a very, very good process. I guess it's a step towards really becoming professionals into whatever you guys decide to do. So, sorry, that's a little sidetracked. Today we'll talk about heat treatment. So, what happened so far in 6 lectures, we went into the casting and then saying, as cast structure is not always good. Sometimes you want to deform it, blend it, and that's where forging comes in. Blacksmithing and all of that, like why we're doing all these things. So now we will focus on why you do heat treatment after you have the shape. And in my introduction, I've already mentioned about the difference between steel and aluminum. So today we're really going to dive a little deeper, and I hope that that's what you get out of the class, that you'll remember a little bit what are the differences. And we'll throw some numbers. Maybe we start right there. So if you're taking a steel composition that is weldable, so something that you can use and make chairs out of and all sorts of things, you can vary your strength in the range, and we'll do it. So let's say it's just anneal, for lack of a better term, or normalized. Let's say you start at around 30 KSI or 200 megapascal. So these are very approximate number. It's not bad. I mean, if you have big beams, structures, bridges, you try to go a little higher than that. So typically these days, through a little bit more deformation processing, a little bit alloying, you'll go and have what we call a grade 50. It's being used a lot more and more these days for efficiency, if load does matter. So what that means when you say these, or it's in KSI, just the way it works, we're in the US, and it will be, let's say it's specified by ASTM a lot of times, or API. So these are group association that make these standards, and it's a minimum. So you shouldn't be getting a piece. It's not a typical value or anything you get out of the lab. So what happens is you expect these strengths to be slightly higher, or let's say 10, 15% higher is typical. It doesn't mean you don't have one that's very, very close to the minimum. It doesn't mean that if the quality control was not sufficient that you don't have it below, but you shouldn't, because that's the requirement. It's a minimum. So what can you do from there? With almost the same composition, I mentioned yesterday that you can cold form it to become a very, very high strength. So we started putting numbers here. So let's say I cold work and heat treat very fine wires to do the pre-stressed concrete cylinder. That's something we discussed this week. We said we're going to go, to the 150, 200 KSI strength before you break them. It's the same steel. So in terms of cost of getting the raw material, it's almost the same. Now, what happens here is not just gaining. So you gain on strength, but you lose in ductility or toughness. So these very, very high strength wires, they're more susceptible to the environment. They can't necessarily tolerate moisture very well. They also are sensitive to, if you have a catalytic protection, so a corrosion protection system in place, you're more likely to break them if you have a damage to your coating. So you become a little bit in a more sensitive situation where the conditions needs to be good. You get to these high strength level and you cannot galvanize the steel because otherwise in certain environment, you'll create hydrogen, it's going to cause it to crack. So all I'm saying is it's not because you have this ability that we use it a lot of times. We only use it in special conditions. So factor of 5 to 7 in yield strength, so the amount of stress it takes to start yielding for almost the same composition. What should I say? I think I mentioned to you that I've been more and more involved with pipelines. So what happens there is they've been traditionally using something of the order of 50. And with new development, even though we don't talk too much about metallurgy these days, there has been development over the past 20 years to go beyond that and still be safe for the majority of situations. So now when I graduated, I think it was grade 60 or 65. Now, the past 5 years, grade 70 became a little bit more the standard for new installation, and it keeps going up. There's people talking about grade 100 just for oil and gas pipeline. If you're talking about drilling, they are in that range of about 110, 120 KSI. So you'll see all that range. And what happens is they're willing to replace components, inspect components. So if something develops, it's not used for a long time. And that's how they deal with the possibility of having cracks. If it breaks during drilling, they have to come and fish the tool out of the hole and continue on. So it's not like an airplane that falls down. Talking about airplane, even in airplane in the landing gear, you have components that are in the 100, 120 KSI yield strength, so almost 1,000 megapascal. And these actually have a good combination of strength and toughness. So we're talking, let's say, this is just a side note. So on a 4330 steel, for example, you spend a little bit more. So it's not just a normal steel. You had a little bit alloying element that helps you get a good combination of strength and toughness. So what I figure I'd do today, before, again, getting too much into the details, is show you what toughness means. These are specimens that were Sharpie tested. Do you know, anybody knows about Sharpie? You did? Good. Okay. So it's just a rectangular bar that has a notch in it. So I'll start trying to do this. Okay, I can. So let's say just a rectangular bar that is made with a notch in the center. And you come and hit it from the back side here, and it's going to split open. So we have one here that's split in a relatively brittle way. So you can see it's still pretty square, and the fracture surface is rather shiny. And then you have another one that didn't break all the way. So it stayed connected. So in terms of this test here, it's not overly sophisticated, because so long as you can get a piece of the material you want to test, you do this machining, you hit it, and then you measure the energy involved in creating this fracture or creating this deformation. And it just speaks to a combination of yield strength and toughness, but a lot of times these alloy that have a higher yield value, they will break more easily under these conditions. And then there's also an effect of temperature. And I get more into this when we talk about the use of structural material in the spring. But I just figured circulate it, get some sense. So with respect to aluminum first, so today we're going to do aluminum first just because it's simpler. And I know you'll understand the steel as well. So again, we're just going to contrast the two of them. With aluminum, what happens is you want to form precipitates to increase the strength. So let's say the Aluminum Association will give you a certain grade of chemistry. They'll say you have a 1000 series alloy that's almost pure aluminum, and then you have different categories. Let's say that you're making a sports boat, you may use a 5000 series. If you're doing a construction, you can decide to use a 6061. It's very common. If you're in aerospace, you're looking typically it's 2000 series, 7000 series. Well, all I want you to know for today is these guys are the one that we're talking about today with respect to heat treatment. And they all work almost the same way, where at high temperature, on a phase diagram, you're able to have a single phase. So it's almost like a liquid. Everything that you put on, let's say it's copper, magnesium, anything that goes in there is in solution. And then when you lower the temperature, if you do it slow enough, you have this phase transformation where all of a sudden you got two different composition. That requires diffusion. So if you take one of these alloys and cool it quickly, so you quench it, you freeze the structure you had at a high temperature so it stays in alpha. It's super saturated with copper or magnesium are very common ones. And one of the reasons is you can't easily get this process of forming the precipitate. There's a certain energy involved. We discussed it at the very beginning. When you have a phase transformation, now all of a sudden you have new surfaces. So you need a certain volume to randomly happen to be there with the right composition. So you need, let's say you have copper, all of a sudden all the copper needs to move by random walk to that location and have a critical amount of it. So it makes sense that when you're doing it too quickly, it doesn't happen. So this just shows a little bit the effect of your cooling temperature on whether you'll have the formation of precipitates or not. So you can see that if you're just a small amount in this range here, just a small amount below the equilibrium point, there's no nucleation because you don't have enough driving force. So you need to be, 100 or 200 degrees of temperature below here to really have the action of the small precipitate taking place. Because it's solid. So when it's in the liquid, it's very, very different. But in the solid, that's really where you have this effect of temperature. And you need super cooling, if you will. You need to be much lower than the critical temperature. So these are just concepts I want you to keep in mind. So now let's get down to more what happens with our aluminum alloys. We have this alpha phase to the left, and then we have cooling at 4 different temperatures. You see the lines there. That leads you to different precipitates. Okay. So what does that mean? When you're trying to form these nuclei and all that and become a stable phase at lower temperature, you cannot diffuse as far. It's just the way it is. So the same way that close to the equilibrium here where you have enough temperature, all you have to do is make this condition of nucleation happens because it's a small driving force. You're just below the transition. It's a small driving force, so you need a big precipitate to start the reaction. It will take time. When you get to very, very low temperatures, so the GP zone here, what happens is you have so much driving force that you can start with something a lot smaller. So the types of precipitates are completely related to the temperature that you're forming them at. So if you form them at lower temperature, they're going to be a lot smaller than if you form them at higher temperature. What are the consequences? Okay, so for the heat treatment, it'd be very hard to try to cool the aluminum to say I want these prime precipitate or double prime precipitates here. It'd be very hard to get to that temperature and then stay there. So that's where the typical quenching procedure in water or for aluminum alloys, typically it's in oil, so it's not as severe, it doesn't cause as much distortion, and it's sufficient. What happens, you freeze it, and then you reheat it to the temperature you want the transformation to take place. So I hope it doesn't look too complicated, because it isn't. If you make a part or you make a big extrusion, you gotta quench it to some extent, and then you heat it back up at relatively low temperature. We talked about 300-400 degrees centigrade. I'll give you a side story to that, is because it's so common with the aviation and the aircraft alloy. I've been involved on the projects where they have a heating system in front of the wing for ice storms, so you don't have buildup of ice over the leading edge of the wing. And that means they bypass the air from the engine that goes back into these channels. And it's not a precise science in the sense that they open gates and they get the air to circulate, and the temperature can be, I was told, up to almost 200 degrees. So what do? You either make sure that your aluminum is not going to lower in strength or change in those temperature range, or you use another alloy. So, and they were doing a combination of the two, so it wasn't anymore just a design based on strength, it was a design based on making sure that the aluminum alloy is not going to change during service when you use this system. And for the primary structure of the wing, they ended up deciding to switch. They didn't feel comfortable using aluminum in that region, so they moved to titanium, and that was expensive but necessary, just because it's a difference between the skin and the primary structure, which caused some issues in terms of connecting it together. So why do we form precipitates? 2 weeks ago, we talked about dislocations and how they are a little bit like a fold on a carpet. They allow you to have a shear movement within the crystal at low energy. I think we can all imagine that if you have these tiny precipitates in the crystal, they are obstacles. They're going to impede the movement of the dislocation. But, and this is really important, it will only matter if those precipitates are part of the crystal. If you recall the lecture where we were talking about grains that were pretty big, and then all these dislocations being much smaller loop inside the grain, well, if you at high temperature, when you form the precipitate, what happens is you form your precipitate here, next to the grain. It's not part of the crystal. So it's not going to give you any strengthening whatsoever. The way to get the strengthening is to have these precipitate, let's say this is the double prime, that is coherent or semi-coherent in the crystal. And therefore, they have to be small and they have to be distributed. And we call them a distribution. You don't see them under the regular microscope. You have to go to a transmission microscope to see them. So the same land scale as where all these dislocations are. And there is an intermediate size of precipitates. That's what you see in this hardening curve. So let's try to explain this plot. What happens is you start with a quench condition. Then you start heating up to form the precipitates, and you stop. Take a sample and test it. In this case, just a hardness test. So you see that depending on how you age the sample and the temperature you're at. So the higher temperature, of course, you go to a higher hardening. At the lower temperature here, you haven't passed the peak yet. You're still on the what you call underage condition. So it's a little bit how you able to establish the peak in strength, if that's what you're looking for. A lot of times we'll want it slightly underage or overage, or maybe we don't want any hardening at all. But typically with these alloys, because you spent the extra money on yellowing elements, you'll want to heat treat them to a specific target. So when you get to that downfall here is from the combination of the smaller precipitate to make bigger one. It may be a little counterintuitive, but hey, it's all dynamic. Everything vibrates in there, and it will go for the lowest energy. So if two precipitates are close enough, by a random walk, eventually they'll combine. There's going to be this diffusion process to combine, and then all of a sudden you lose your straightening effect. So I guess, from my standpoint, it's relatively simple. Your matrix is still soft. All you did is you put these obstacles that are part of each grain. Any questions? I did it faster than ever before. Do you want to use any aluminum for your project? You want to worry a little bit about the welding of aluminum. It's a little bit more sensitive, it can soften the aluminum quite a bit. In terms of strength level, and that's something I'll bring tomorrow, because there are a few cases where you do want this type of strength, low strength aluminum. I've seen it 2 or 3 times. Let's say here we're looking at 3 to 10 KSI, roughly. I mean, these are all rough number. Then when you're in the aerospace grade, let's say I'll do 30 to 60 as your yield strength. So pretty good significant here again. And if you go to a machine shop and want something done, a lot of times they'll give you the 6061 T6, which is closer to that range, but definitely harder than a mild aluminum, because it's not too hard to machine, it's not too expensive, so it's a good thing that they keep in stock a lot. But it's not, this specific one is not used so much in aerospace, doesn't have a very, very specific thing that's optimized, whereas those two categories, one is better for yield, the other is better for toughness. And that's why they use both, depending on the position you are on the aircraft, what you're looking for. So none of this is crazy expensive, but of course, when you start talking about large quantities, it starts to matter. So I had a project on wind turbines where they want to put a shroud to essentially make the wind turbine a little bit like a turbine engine. So it has a shroud around it, you funnel the air in, and there's one of those close to the airport here at Logan, and they've made quite a few of those. You can make them much smaller because they funnel the air in, and it's a new company, so they want to make sure their product looks good. They didn't want steel, thinking that it's going to rust. But then when you get into pricing and making these big 100-foot diameter structures, it just wasn't realistic to do. So we highly recommended they use steel, and if they wanted to make a good life, to galvanize and paint it. I think they did, but they were trying to think about what if we do it on composites and other things. Just looking into a lot of avenues. This is a special project I worked on. It's here in Massachusetts. They call it ditches or domes to look over, you know, the Cold War and all those things. And I was not a citizen back then, so I couldn't tell what they were doing. But looking into the extra space, so you can see that under the proofing, there is this structure that has a very, very special shape to focus the signal from the extra space into a sensor. So the sensor in this case is mounted up in front, and all that structure does is just resonate the signal and condenses to the sensors. So in a structure like this, it may not look super obvious, but weight does matter. If you make that structure out of concrete, for example, reinforced concrete, you can probably get it very, very stiff. You can do whatever you need to do, be cheap. But then what kind of foundation are you going to need to support it so it doesn't move over time? I think the answer is you have to go to the rock bed, and then you start becoming sensitive to seismic event or vibration you have down there. So anyway, the engineers that have been working this for 40, 50 years, they made this commitment that they will have a sort of a floating structure on ground, so a little bit like a house. When you build a house, you don't go to the rock bed. If you do a skyscraper, typically you do. But so they decide not to go too deep, and then have a structure that's light enough so seasonal changes don't cause trouble. What else you need? You do need stiffness. Why you need stiffness is this condensing of the information from the extra space is dependent on having a very, very specific shape. Now, how you get the shape in practice is a lot of aluminum tubes. And this is actually typical of what they had there. So you can see, maybe, I think they had up to 11 or 12 tubes coming together in these types of joints. So it's essentially hollow, and it has this joist type of reinforcement. So it's very resistant in bending. So a joist will have a top chord, a lower chord, and then you have diagonal, and it's give you a good combination of low weight, low cost, and stiffness. So the goal with the ditch was strength, so it sustained its self-weight. You also needed to be stiff enough so the shape doesn't change. You had a small allowance, because what they did is they would have these little motors that they could use to make some small variation to the exact shape. It was the practical way that they had, but there's only a certain range there to take the inner surface and change the shape relative to the substructure. So I've worked a lot on these joints, and this is actually a topic more related to welding, but you see it here. You have all the tube coming together being welded. Well, guess what happens to your heat treatment? You lose it, right? You reheated it, you remelted the whole thing. And it's one of the main reasons why if you have an aircraft, we don't do welding, because you have so much reduction in strength. So it doesn't matter all that good stuff you did here if you end up melting it and having this cast structure at the joints where the load is the highest, typically. Not always, but in this case it is. These tubes, if they buckle a little bit, it causes bending at each end. If they pull on it, there's going to be a certain eccentricity there. So one solution, and I have to bring it next class, is to use what we call gusset plates and essentially change the mode of loading of the weld. So instead of being welded all around, it's welded along the length here, and it's loaded in shear. And I got some example of that. Sometime when you see it, it's how you can remember it best. This is actual data collected. It was sort of fit curve, but as to what happens to your strength in welding relatively high strength aluminum. So it was a 6061 T6. So what we talked about was used a lot for just general manufacturing. So you can see in yield, there's a plateau right here. It's 40 KSI in the tube. And then the tube material that got heated from the welding. So this is not fused. This curve here, oh boy. Good. The curve from 40 to 15, what I want you to keep in mind is it was not melted, just heated. But heated high enough, if you remember a phase diagram, that you got back into solution. So you re-diffuse all these precipitates, and you cooled back fast enough that nothing reformed. So you're looking at very low strength. And the consequences of that is, first of all, it will start deforming and yielding a lot sooner than you thought. So you'll have a little bit of a change in shape when you reach loads that exceed that. It's not really breaking because it's very ductile, it's just soft. But you have a little bit of a stretch. And you have low fatigue resistance, which is just a resistance under cyclic load. Because each time you come and deform and yield it a little bit, then you start forming cracks very easily. So if we're talking about a nominal strength here, let's say we pick 30. It shows 40 there, but let's just pick 30. If you weld it the way it is here, and you know you're going to have a lot of cycle of the ditch looking up, looking to the side, looking up, there's a lot of movement involved and changes in load. The code will give you an allowable stress of the order of 2 to 3 KSI for your cyclic load. It's crazy. Because now you're becoming closer to what you had originally on a pure aluminum. It's very, very low straight. And if you don't respect that, it starts cracking. And it did happen on some of these projects that before they started realizing fully why you have this. You have this because of the welding and because you have cyclic loads. If you don't have cyclic load, you're able to take a little bit more, especially if you're willing to deal with a little stretch of the material. And we will talk about welding tomorrow or Friday, but I think that gives you an overall perspective. So aluminum precipitates or dispersion, and it's not permanent. If you reheat it high enough, you lose it, and that happens in welding. And if you have an application that involves high temperature. Steel. All right. So the situation with steel is very, very different because you have this phase transformation. So let's see. When you heat treat the steel, you go from one phase here, and the phase diagram doesn't quite continue. It's discontinuous. You have to transform. And it means that the structure changes. If you had pure iron, it will transform also. So this structure, if you just look at the black atoms, is the high temperature austenite phase, the red steel. And then when you go to the lower temperature, it looks like this. And this is not as ductile. There will be some stainless steel that by the alloying, they stay in that shape. And those are the ones you want to use for low temperature application. They remain very soft and ductile. So that's a 300 series stainless steel. It just stays like this because of alloying. But the case we're talking about today is either you form this or you form something else. And that has a lot of implications in terms of your strength. And so the slow cooling gets you to form this lamellar structure, and I'll show you on a video or an image here. So these are different types of structures that you're going to form when you're cooling steel. And by the way, it's a way you can figure it out after the fact. What was done is you cut and polish, and you look at the microstructure. Oh, these are big grains. They have the lamellar structure. So lamellar is very fine, but you can see it here that it's not all black. It's got some black and some a white portion, and that's the perlite. So what happened is you started with this that had a lot of available space. So these are the little brown atoms for the carbon. And when you get to that critical temperature, because this phase doesn't want to continue this way, when you try to move to this phase, it turns out there's less room for the carbon. So you'll have to form that second phase that's carbon rich, that's the cementite. So you end up with kind of almost pure iron with cementite as a lamellar structure. And it's what gives you this 30 to 50 KSI strength. It's not bad. It's a little bit like a composite. And that's why it's different to have steel than just pure iron. But it doesn't have the strength level that you can get through these other heat treatments that we're going to go through now. So the heat treatment gives you these types of structure. It's just a very, very, very different. So here you see a pattern. They look like needles, and probably is a good intuition when you think about needles and things that are just very sharply done, like the breaking of a glass. It happens very quickly. So these things, they just form really, really quickly. So it's a military transformation of taking this structure and going to a tetragonal phase. So one direction stretches a little bit, and it gives a few sites available to put the carbon. So there is no diffusion. You're not going to form any precipitates. Everything is, they call it diffusionless. I mean, there is a movement. There's a jump from whatever random location to one here, but it's so, so small. Now, it's not perfect, because you can probably see it in your mind that if I'm going to go from a regular cube to a tetragonal, it means that one direction is stretching and the other is contracting. It's just the way it is, because the average distance between the atoms is going to stay about the same. So there is a volume change of about 4% involved, and you can't all do it in one way. So inside a grain, you're going to have to go one way, the other way, the other way. So in average, it gives you the typical behavior. So that's the reason for the needle type structure. Sometimes it looks like a lamellar structure, but the main point is it's a diffusionless transformation. I mentioned at the very beginning of the class that this comes back right now that we kind of understand better the context. You change from a cubic structure to a tetragonal. I'm sure we can all agree that that's not exactly as ideal for moving the dislocations. There's just less room, less opportunities, just like a ceramic crystal doesn't deform as easily. So when you go from the cube to that tetragonal structure, you lose a lot of what we call slip planes, so place for the dislocation to go. So your strength, way up there. So if you didn't need ductility, you could keep it as is, but the point that I've made earlier, and this is a good place to emphasize it, is it's not a practical structure in most cases. It's just too brittle. It will just literally snap on you on this sample I circulated. So you do what we call a tempering. And I don't know if it's intuitive, but so in this case, the tempering purpose is to soften back the structure. So it will retransform, at least partially, depending on the condition, towards the equilibrium structure. This is this one, but at a much finer scale, because you're doing at a low temperature, and you're able to stack these layers of cementite with the pure iron at a much finer scale, so a lot higher yield strength. It's equivalent of making very, very small grains out of a big grain. So those are called tempered steel. And if you go through just a typical supplier, they'll call it QT. So let's say you have a QT 125 is used, let's say, in the drilling industry. So quench and tempered at 125 KSI yield strength, pretty high. Do you need to go through all of that? No, a lot of times you don't. So again, most buildings will be in that range. Automotive type, maybe a little bit higher, but it'd be rare that you start getting into these significantly higher strength. You'll use them in pre-stressed concrete. They'll go through all that process of heat treating it, because for the same amount of wire, you get a lot more strength. And there's only so much reinforcement you can have if you want to still have the benefit of being concrete. So what happens on, that's something I went over earlier, is you wrap the steel over the pipe, but if you have a continuous wrap, then you don't have the corrosion protection from the concrete around it. So there's only so much steel you can put in. That's why you go and spend the money to put higher strength steel. I don't know.
So this is like kind of my first time learning about steel.
Yeah.
Could you just talk about like the names of the faces? Like,
the faces? Yes. Okay. So for steel, we will have the alpha face. That's just pure iron. And then when we are at high temperature, it's the gamma that we'll call the austenite. This one is the FCC structure, and this one is the BCC. And then the martensite doesn't have a letter, so we'll just... And that was a joke when I was an undergraduate. Apparently, in a lot, including among engineers, you can look very smart if you say, well, does your steel contain a martensite? Because nobody knows what it is. So that's the tetragonal here. So I think it's a body-centered tetragonal, but I can't say for sure. I think so. So body-centered tetragonal, or something equivalent. And the transformation temperature from this one to this one when you're cooling, or the other way around, is around 700-800 degrees centigrade, and that's roughly where the steel becomes red just because of temperature. So you can have the austenite at ambient temperature, depending on your alloying and what you do. You have to stabilize it, essentially. And that's what happens when you add the nickel and the chrome and those guys. I think it's mostly the chrome. And that gives you a low temperature ductility. So the main reason why we invented the Sharpie test a while ago, well, it was the failures, but other than that is because steel, conventional steel is the base centered cubic, so that at some point the yield strength goes way, way, way up because the dislocation can't move in it. And we could go over that, but that's a little bit more tricky. There's one type of dislocation that just becomes very dependent on temperature actuation, and that's a particularity with the BCC structure. Does that help? And some of these are noted there, and I guess what this shows you is, depending on your alloy, you can, if you play with your alloy, you can get a certain cooling rate. Let's say you talk about the blue curve here, where you'll form what is called the bainite. So the bainite is just a more refined structure that you can form all at once upon cooling. The only trouble with this is your cooling rate is different on the surface of the part than in the center of it. So you can try to optimize and hit that good structure, by just cooling. So you'll save a step. You'll save the step of quenching and then heating back up. But then you have to agree with yourself that this is always going to give you the structure you want where you need it. And a lot of times it's not just the surface strength and toughness we worry about, it's through the depth, because if you're going to have a small crack, then eventually it's going to break through the center. So this is something we did cover very well yesterday. So it's one reason why the concept of trying to do it all at once is not used as much. So a lot of times you go and you cool it fast enough so you miss these transformation that would otherwise take place over time, and then you reheat it to get to those. It's all about homogeneity, the reason why you do it in 2 steps. Otherwise, you could try to do it all at once. So I hope that helps. And again, I'm here if you want to talk about the project, what we went over yesterday, anything. Thank you.